Hey, welcome back to Math with Patrick. Today is September 6th, and we're solving problem number 249 from the Daily Epsilon calendar. And with all the other problems in this calendar, if there aren't obvious instructions, it's assumed that we're solving for x, and x should match today's date, the 6th. Though when I'm solving it, I usually like to not know that the answer is 6 and try to come across it on my own. So I see some kind of initial condition that says x and y are elements of the integers. Essentially, they're the whole numbers and they could be like positive, negative, or zero. And then I have some kind of equation here where y to the power of x minus x to the power of y is equal to this product of 47 and 167. I believe both of these numbers are prime. I would need to do some divisibility tests on them to be sure, but that's my hunch. Is that if it's in some kind of factored form like this, and they both kind of look prime, I'm guessing they are, and maybe it'd be nice to know what this number is. So let's just real quick do that multiplication, and see what number it is. So there's the 49. That's 42 plus 4 is 46. That will make an 11. Placeholder 0. That's a 28. This is a 24 plus 2 is a 26. That is a 4 plus 2, which is a 6. And so we get this number right here, 7,849. Okay. So how do we do this? One idea that I have is that we could isolate y or x, because then maybe we could have it be a function between y and x, and we just plug in some x's and see what happens to the y's, or vice versa. But I do know that when when variables are in the exponent, and also when variables are kind of connected to each other through exponentiation, it's really hard to get them apart. The opposite of exponents is logarithms. So maybe we could try taking the log of both sides, kind of like this, and this would still be a true equation. But I don't know how to break this expression down any further. There are some log rules that I could use in other situations. I know that the difference of logs is equal to the log of a quotient. So this is a rule that I know, but I don't have any rules that let me split up subtraction on the inside of those parentheses or in the argument of the logarithm. So I don't think I can isolate one of the variables. Another thing that I kind of want to explore is the fact that they're both integers. And so we could see what happens when values are negative or 0 or positive. And also, it might be useful to think about if the numbers are even or odd. Let's actually do that first. Let's make a little table. Let's put y and x, and then this expression right here, y to the x minus x to the y. And just for simplicity, I'm going to assume that these numbers are going to be positive for a sec, because I know that negative exponents are going to do some kind of funky things. So let's assume for a sec that all these numbers are positive. I want to know what happens if they're both odd, if they're both even, or if we have one even number and one odd number. Well, if they're both even, then we have an even base to an even exponent. So you can imagine 2 to the power of 4 or something. And we're just going to be multiplying a whole bunch of 2's or a whole bunch of even numbers to each other. And so this term right here would become an even number. And then the same thing would happen to this guy. And then once you do an even number minus an even number, you still get an even number. So actually that's this entry right here. And we'd get an even result. And knowing that our product here between these two odd numbers is still odd, I know that x and y can't both be even. And so this scenario, I don't even need to think about. Likewise, with the odd and odd numbers, you can imagine maybe 3 to the power of 5 and then 5 to the power of 3. Both of these are going to be odd numbers as well, because we just have a bunch of odd numbers being multiplied on both of these, and an odd number minus an odd number is going to be an even number. So this also is another scenario I don't need to worry about. Essentially, the parity or the even oddness of x and y is going to be different. One has to be even, one has to be odd. Also, one thing I noticed when I was doing this example is that right off the bat, I don't actually know which one of these is bigger. I think 3 to the power of 5 is because we're like doing more multiplication over there. So I do think this like could be, or yeah, it could be positive because this one's bigger than that one. But I don't actually know what this looks like off the top of my head. And so before I keep digging into it, I am actually curious, when is it that y to the x is greater than x to the y? And I figured we could hop over to Desmos just to visualize it. So here's y to the x, and we're wondering when it's greater than x to the y. And we get this kind of interesting, like somewhat symmetrical picture in the first quadrant. What's interesting though is that nothing shows up when either number is negative. So maybe we should dig into that a little bit. But I'm noticing that we essentially have two regions, either like x is small and y is big, or x is a little bit larger than y. So actually, that makes sense, right? When I said that x is a little bit larger than y, that kind of confirms this like 3 to the 5 and 5 cubed example, where when they're kind of similar in size, then this inequality holds true when y is the smaller value. But then there is a little bit of an exception kind of over here. And also this kind of like central dotted line right here makes a lot of sense to me, because if I'm allowed to have them be equal to each other, then we're going to fill in that line. And this is just the line y equals x. And what this shows me is that these expressions are equal to each other, like y to the x and x to the y are equal to each other when both numbers are the same. And that makes sense to me, so that then when we remove that equal sign, the dotted line shows up. So it just shows me that I can't actually lie exactly on this line. I have to be somewhere below it, which I guess doesn't really matter for this problem, because earlier I said that like odd or even pairs just won't work because our target number is odd. And so I guess that actually doesn't end up mattering because we already proved that it can't be on this y equals x line. So maybe let's just kind of methodically look through this graph. Let's look at pairs of numbers that are different in parity. And let's look maybe low to high in terms of x. So here we could actually even create a function f of x comma y equals. And then there's the difference. I still actually like having that inequality show up on the graph just to help me like know what numbers to plug in. And basically, I just want to find the right numbers x and y to plug in here to get this target number. So I think it would make the most sense to just try to set one of these numbers equal to just some number right now. And I want to choose x just because that seems like it makes sense to me. And I want to choose 0 because, again, not thinking about the negative numbers for just a sec, 0 makes sense to me as like the starting number. And so if I plug in a 0, I will get y to the power of 0 minus 0 to the power of y. And for most values of y, this is just going to be the number 1. Because like there's a rule out there where like anything to the power of 0 is just 1, and then 0 to the power of anything is just 0. So anytime we have this kind of setup where we're plugging in 0 for x, we're just going to get the number 1. And that's nowhere near 7,849. The only caveat is that 0 to the 0 is undefined. I don't know if Desmos will actually say that, so let's try it. F of 0 comma 0. Okay, so it's actually giving me a value because I think internally it's doing 0 to the power of 0 minus 0 to the power of 0. And like since these numbers are the same, subtracting them gives you a 0. And I guess it is even saying that 0 to the power of 0 is equal to 1, though that is a little bit incorrect, just to show you. It does approach the value 1. Like here we can kind of see that as x gets closer to 0, the value gets closer to 1, though this is more of like a limit idea rather than an actual true value. Regardless, if we do plug in a 0 for x, then most of our outputs are just going to be equal to 1. And that's nowhere near 7,849. So we could try incrementing x to be 1 and then plug it into here, kind of fill in all the spots where we see x. We get y to the power of 1 minus 1 to the power of y. And, well, y to the power of 1 is just y, and then 1 to the power of y is just 1. So we do get y minus 1 right here. And I'm curious when y minus 1 is equal to this target value. And I mean, I could just add 1 to both sides, so y could be 7,850. And I don't see anything wrong with that, because if I try plugging that into my function, 1 comma 7850, I do get my target number. So this is a potential answer to this problem today, just by like kind of doing a smart guess and check right here. We found an answer, but x is 1 in this example, not 6. So I guess this calendar problem is a little bit wrong in that there are more answers out there than the intended one. I feel like soon enough we're going to get to x equals 6 and find that solution as well. But that's very interesting that we have an odd number and an even number following the rules as before that satisfies the problem. So anyways, let's try when x is 2, and we can see visually on the graph that 4 isn't a valid number and 2 isn't a valid number. And so the only possible whole numbers or integers that we could plug in, well, there's just one, it's 3. Fortunately, it's odd, so we could try plugging that in, 2 comma 3, but that gives us the number 1, not 7,849. So we can rule that out. Looking at the 3 column right here, it doesn't look like I have any whole number kind of spots in my inequality, so I can skip it. 4 just has this whole number 3, so I could try plugging in a 4 comma 3, that's 17, not 7,000. 5 looks like it has some candidate numbers, like I could plug in this 2 or this 4, so we could try that. 5 comma 2 is way too low. 5 comma 4, still kind of too low. And then with the 6, we can't plug in the 2 because those are two even numbers. So we could plug in the 3 or the 5. So we could go 6 comma 3 now, and then 6 comma 5 also hits. Cool. So there, I think, is the intended solution. This is when x is 6, which matches today's date. This is when y happens to be 5. And we do get this number right here. Interesting, though, that there are 2 solutions already, and we've only really looked at like a few numbers for x. So what we could do is actually keep using Desmos to help us guess and check. Desmos helps by like putting a point on the graph, and any one of these points we can plug in to our function, a comma b. And so as you can see kind of in that corner right here, we can see the value change as I move the point around. So it looks like any number kind of in this like C in the middle is just going to be way too big. And it looks like the number is decreasing as I kind of move left. Looks like it also decreases as I move down. So it looks like it increases as I go up or to the right. Generally, I guess. Maybe there's different behavior kind of somewhere in here. But generally, as I move up and to the right, these numbers get really big. So that's kind of an idea as to why I might not find around 8,000 out here. Though I guess if I move left, maybe I would have some possibilities as I get kind of closer and closer to this line. Anyways, a and b should be fixed to integers, so I could put this little step to 1 for both a and b. And that just means that as I step between values, I'm jumping by the value 1. And so now I'm fixing myself on the integers. So if we go here, there's that solution that we already found. And so we could do a methodical search the other way, perhaps, just to see what happens like as we go like down, up. So we could start when y is equal to, I guess 2 would make the most sense. And we can see that as we move to the right, these numbers are increasing. And then I think right around here, now here, yeah, we jump over the value like 7,849. So we probably encounter that number somewhere between here, but it's not going to be an integer solution, so it doesn't count for this calendar. Going up to when y is equal to 3, we could kind of look around until we jump across that 7,000 value again. So we're probably going to find another solution here. Again, not in the integers. Moving left again, this hops over 7,000, and then this one hits it exactly. And then if I try moving up to the next one, then see how this number is already bigger than 7,000, and when I move left, it hits 0. So I'm pretty sure all of these are going to do the same thing, where we're, again, probably going to find some kind... Oh, actually, hold on. I could just graph y to the x minus x to the y equals, and then 7, 8, 4, 9. There we go. And so this curve describes all the spots where we are going to find a solution. So going back to say like this one, I think I was hopping over the value here, and now we can see that it does hop over that line. And then this one also hops over the line. If we zoom in more, we can see that it doesn't actually hit an integer spot right there. So this is more confirmation that all the other potential solutions, which there are many in the real numbers, there aren't going to be any when we are just looking at the integers, though. So I think that covers it for this region, because we're always going to be, I think, between 2 and 1. I think there's some kind of horizontal asymptote going on right here. And then we also know that this curve looks like it approaches y equals x so quickly that there's almost no chance for me to find some kind of integer solution up here. So that really only leaves the negatives. And at this point, I can kind of clear that inequality because I'll start exploring elsewhere. Again, I'm still looking at this value right here. Let's see what happens when we hop over. Okay, we got a whole number solution there. 2, 3, 4, 5. Okay, so this one just counts 1 by 1. Hold on. Then won't I just be able to count all the way to 7,849? And it looks like this number, its absolute value is 1 greater than a. So if I do 7,848, that's another solution. F of negative 7,848, comma, comma 1. Okay, and I just want to plug those numbers in just to see if it makes sense. X is this value, so I'll plug that in here and here. And then Y is 1, so I'll plug that in here and here. Yeah, this makes sense to me, because 1 to the power of anything is just 1. And then since we're subtracting a negative, we actually do get a plus sign here. And then power of 1 doesn't do anything. So wow, there's a third solution in the integers, and we had to search in the negatives. That's kind of cool. Let me get that point back on the screen. There it is. Maybe if I kind of search downwards, I'll find something as well. Where's the value? There it is. 0 is what I'm looking at again. And then here, looks like we're alternating between negative and positive. I'm assuming these are rational numbers, yeah. But it doesn't look like we're sticking around with whole numbers, or rather integers now that we're in the negatives. And so looks like I get some zeros when they're both the same, although do we really trust that? I mean, actually, yeah, I think we can trust it this time, because it would just be, the same number minus the same number. The thing that I wouldn't trust is that this is actually the number 0, because I would call it undefined. Anyways, so we found a solution here. If we jump up, we are getting more rational numbers. If we jump up again, we get more rational numbers. And if we look this way, we get more, non-integer solutions or non-integer outputs for this function. So, I mean, at least for now, I didn't check this quadrant. Got it. We got some negative integers counting up, so that'll never hit a positive integer. And then we got some more rational numbers as we keep kind of searching around here. So I'm not entirely sure if these are our 3 and only 3 solutions, but I am quite happy that I found this one, because I feel like that one's a little bit hidden, right? Hiding in the negative numbers. And I'm also happy that I found this one just because it kind of shows that the answer, both of these show that the answer today is, or the calendar problem today is a little bit wrong because there's multiple answers. So anyways, let's go back to the whiteboard and kind of finish the video. So here are our three solutions written out on the whiteboard. X could have been 1, X could have been 6, or X could have been negative 7,848. So this problem could have corresponded with like September 1st or September 6th or September negative 7,848, whatever day that is. And I said earlier that this question was wrong just because other questions in this calendar have really done a good job at trying to remove kind of these extraneous or like secondary solutions. So they really should have put some kind of condition like X is greater than 1 or something. That would have been totally fine. But since they didn't, we do have 3 separate solutions. And now I don't know what day it is. I'm kidding. Anyways, we did find the answer though. Here's the intended solution where X is equal to 6. That does match today's date and we can be all done. So thanks for coming along and watching this video, and I'll see you tomorrow.